Everyone, we are back, and let's go ahead and do our Pset 3. So we need to look at the image below, figure out some vacancies, find the 0D defects. So actually, let's go ahead and list the dimensionality of the defects right now. So we need to figure out the dimensionality of the defects. So vacancy, 0D, self-interstitial 0D, impurity 0D, 0D, edge dislocation 1D, grain boundary 2D, void 3D, and then 0, 0. So those are the dimensionalities. So do we see any vacancies? Yep, right here. That's a vacancy. Right there. Are there any self-interstitials? There we go. Right here. Are there any impurity interstitials? Solute atoms. Yep, right here. There we go. Are there any substitutionals? Yes, one right here, and then one right here. Any edge dislocations? Oh, there we go. That's our edge dislocation right here. So there's an edge dislocation. Any grain boundaries? Not that I could kind of see in this picture. So Frenkel shocky pair? Nope. So the rest of them are all 0. Fantastic. So I have 3 different mystery materials, X, Y, and Z. They're all metals. Want to figure out the concentration of vacancies, varies as a function of temperature. So I'm going to pull out my handy Mathematica. Let's go ahead and get started. Mathematica. Very, very fun Mathematica. And, all right, let's go ahead and get started. So if I look at my system here, actually not my system, my Mathematica, I'm going to have 3 different materials. So X, HF, so the enthalpy of formation of that for X is 0.8 electron volts. X, or actually Y, HF is equal to 1.4. And finally, Z, HF is equal to 3.6. My K, because this is EV, I want to do 8.67 times 10 to the minus 5. Let me look at that quickly to make sure that is indeed the Boltzmann's constant in EV per K. Let me check this out. And I'm looking, and I think it's minus 5. Yeah, 8.617 times 10 to the minus 5. Electron volts, EV, basically. EV per K. And I was doing that and making a little comment. And then finally, I've got actually that's it. So let's go ahead, and actually I've got my function. I can create a function, x of v. Actually, let's go ahead, x of v, hf underscore. I want to do my temperature underscore, and then I'm going to do exponential minus hf divided by k times t. And voila, here we go. So I could do now, the question's asking what's the concentration at room temperature? So XHF, room temperature is 298 K. And we get this. Now it changes for Y. Again, must be from 0 to 1. See, much, much lower Y because the enthalpy of formation is getting higher and higher and higher. And then I could do the exact same thing now, but for 1000 K. So I change this to 1000. Woo! Big jump. An exponential, an Arrhenius jump, as we might say. But again, we could see the huge difference with increased temperature. There we go. So how do you expect the concentration of vacancies versus self-interstitials to differ? I would expect them to be much, the concentration of self-interstitials is much smaller. Why? Because we know that the enthalpy of formation of vacancies is much less than the enthalpy of formation of interstitials. There it is. And we see that can make the difference. Create an Arrhenius plot of the concentration of vacancies of each of the 3 materials. Explain how, if you're given the plot, you could find the enthalpy of formation. So an Arrhenius plot is just looking at my ln of xv and then for t. So I could go ahead and it's very hard to make a function to plot the 1 over t's. So what you may do, again, I would be satisfied honestly enough with this, knowing that I know that this slope is going to be equal to, so my slope equals minus delta h over k. But we can go ahead and actually figure out what this function would look like effectively, because actually ln of xv, so this is basically our y, minus delta H F divided by K, our slope, and then 1 over T is essentially our X. So Y equals minus M, actually equals M, X. So I can actually plot that, and it would be, I could look something like this. Oops, it's kind of bring it over here. So for example, I could do, so my phone needs to know how to plot, basically minus X HF divided by K times, just do X. And X goes, let's say I want to plot it from 1K, so 1 over to 1 divided by 1,000. And I can kind of plot that, essentially that value. So you can kind of see what it looks like right here. So 1 second, if someone, we're back from the knock at the door. So I could change this value, and actually I could plot multiple of these at a time. So I could plot the same function here, although it'll be very difficult to see, as you'll see in a second. So it's not super cool. Y, and then I could also do the same thing for Z. We could go ahead and try to see if we can plot these. And you can see the different slopes because we have basically different conditions. So there you go. That's another way to plot this erroneously. So fantastic. So let's go ahead and look. So that is number 3 out of the way. Write the Frenkel. I'm going to actually go ahead and erase some of this on the side here. Write the Frenkel and Schottky defect reactions for SO3. So I know that my S is going to be what? Basically 6 plus. It's kind of a weird one. So my Schottky defect is going to be null, goes to vacancy in S plus vacancy in O. I know this is 1, 2. I know there's 3 of these. And I know this is 1. This 1, 2, 3, 4, 5, 6 right here. So there's 3 oxygens. So charge balanced, I'm basically material or mass balanced. For the Frenkel defects, I could have S X goes to S interstitial plus vacancy of S 1, 2, 5, 6. 1, 2, 3, 4, 5, 6. You see that there. And then for oxygen X goes to an oxygen interstitial, which is 2 plus vacancy in oxygen, which is, so again, 2 minus to 0, 2 plus. Enthalpy variation for Schottky is 0.3. Frenkel 0.1, which is the dominant. It'll be the one with the lower, basically, enthalpy formation. So I Frenkel. All right, now we get to some defect reactions. Yes. All right. So I need to write 3 defect reactions for the corporation of, so tantalum oxide, Ta2O5 into Fe2O3. So let's go ahead and start with, one must include an anion vacancy. So I need an anion vacancy. So I need a vacancy. Again, I can only create vacancy in a host, so vacancy in oxygen is going to be a 2 plus. I could also now, let's go ahead and put, so this is going to be a 2 plus. I'm going to do a cation substitutional. So I'm going to do Ca, excuse me. I'm going to do a tantalum and Fe. So I need to put this one in here as well. So Fe is 3 plus to tantalum, so this is also a plus 2. And then now I could also do, let's say I want to do an oxygen interstitial. So an oxygen interstitial, so I could do minus minus. So I could start to now play around with these guys. All right, so let's say I want to do 2 here. So now this would mean that I could do 2, so that's 4, it's 2. I could do 3 here. Let's see if I could do my mass balance. So I'm charge balanced, that's good. So tantalum oxide, so I've got TaFe, so Ta, 2 TAs, and then how many oxygens? 3 oxygens, I need 2 more oxygens, 2 O. So I'm good there. What about my subscripts? 2 Fe's, how many oxygens? 1, 2, 3, done. So nailed it. Let's see, I need to have a cation interstitial. Ca2O5, Fe2O3. So my tantalum interstitial, so that's going to be 1, 2, 3, 4, 5. Plus, let's go ahead and do, I'm going to do another let's do actually. I'm gonna do another. Actually, I won't quite do that. So let's do the TAE as well. So 1, 2, and then I'm gonna do a vacancy in FE as well. So that's gonna be 1, 2, 3. So I've got 5, 1, 2, 3, 4, 5, and then I've got here. I've got my 2, my oxygens. Actually, I'm gonna do. And then I'm going to add an oxygen interstitial. Why not? 1, 2. So this gives me 5, and then let's do 2. Let's see if I've got it. So 3 plus 4 is 7. 5 plus 2 is 7. All right. So let's do TATA 2 oxygens here. 2 plus 3 OOX. All right. FE 1, 2, and then 3 oxygens. There we go. And then finally, we could do our interstitial, or actually our substitutional. 2, 3, tantalum, Fe, so 1, 2, plus vacancy Fe, 3. I'm going to just do 6. I'm going to do this plus 3, actually 4, excuse me. So 4, so good there. What about my oxygen? So 6, so I need 15 oxygen X. So that would do that. What about over here? FEs, so I have basically 6 plus 4, so I have 10. So actually, let me see here. So I have 6 FEs, so I have 10 FEs. So actually, let me see. Oops, sorry about that. I actually need to go back here and recalculate. Sorry for that little mistake. So I need 2 tantalums. So 2 tantalums, and then oxygen. Oh, actually, I need more oxygens. Excuse me for this little mix-up here. Actually, excuse me. No. I do not need it here. So tantalum oxide, let's just make sure 2 TAs, 5 oxygens. Actually, I don't think that. I want to just double check here. Fe, 2 Fe, oxygen, 2, 3, we're good. Over here, I think we also had the same thing. So tantalum. I just want to double check. 5, 5, fantastic. Fe, Fe. So 2, oxygen 3, boom, we got that. So now we need to do this here. So I need to do 3. That gives me my 15. Again, you should always do these slowly, students. So I've got 6 Fe, I've got 4 Fe, so that's 10 Fe, so 5. Voila. Got it. So let's do the same thing now for NB205 with MgO. All right, so let's go ahead and erase. Let's go ahead and get started. Let's erase. All right, so let's do the incorporations for NB205 into MgO. So one must include an anion vacancy, so I need a vacancy in my anion, so it must be this one, oxygen. So again, 1, 2, plus I'm going to do NB, Mg, so again 2 plus to 5 plus, so that's going to be positive 3, 1, 2, 3, plus I'm going to do vacancy Mg, so that'll cancel out these guys, and then I'm going to do one more. Let's see. Actually, let's go ahead and let's do some counting. So I need 2 here, so that's going to be 6, 8. So how many oxygen? I could do 4 here actually. So that gives me charge neutrality. Now let's do some mass balance. NB, 2 NB. How many oxygens I need? 5. Oxygen X. There we go. All right. So what about MgO? O, Mg. We got 2 here. We've got 6. Yeah. Let me rewrite that. So I've got 6 here. So 2 Mgs here, 4 Mgs here, so 6, and then oxygen 6. Good to go. All right, cation interstitial. So NB205, MgO. I need a cation interstitial, so niobium. Again, 1, 2, 4, 5. Plus, I'm going to do vacancy in Mg. 2, so I need 2 here, I need 5 here. Good. Oxygens, so I could just need that. So I could just do here. I could just do 5 oxygen, oxygen X. So I'm fine across. I'm fine with charge balance. Let's look at my 2 niobiums. Oh, excuse me. Interstitial. Yeah, I got deleted in one. So niobium interstitial, and then 5 Mgs, 5 oxygens. Good. And then finally, the last one must have a substitutional cation. So let's go ahead. So E2O5 goes to O and B for Mg. So 1, 2, 3 plus. I'm going to do actually just simply a vacancy in Mg. So I'm going to do 1, 2. So I'm going to do 2 here. I'm going to do 3 here. 2 Mb plus 5 oxygen, oxygen X. So good. All right, I'm across there. What else is happening? Mgs, I've got 2 here, 3 here, 5, done. So there you go. So we're pretty much good there. Yeah, that's basically your solution. So 5, 6, and done. Hopefully, programmatic notation is now not too horrible for you. And now we need to draw our burger circuits for A, B, and C. So A, I'm going to choose my tangent vector like this. I'm going to start here and count. Go right-hand circuit. This is my start. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So this is no defect. What about here? I'm going to choose it going out of the board here. This is going to be my starting point. So I'm going to go 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then I need to do one more here because I did 4. So start to finish, that is a left-hand screw, anti-parallel. And then here, I'm just going to choose it out of the board here. I'm going to start 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, start, finish. So this is an edge. And that is your problem set. So hopefully this was helpful. Again, go slowly through these defect reactions and you should be good to go. Thanks. Have a great day.